Good afternoon, everyone. My name is Ullas from Rakon. We make oscillators mostly for telecom networks. The topics today is the convergence of the telecom and the data center networks, and then how we see the synchronization techniques across these data centers. Just to give a bit of background, if you look at the traditional cellular synchronization requirements, with respect to a atomic or a reference time source, the time and the frequency gets transmitted across the network elements to the final nodes. Here we are showing the traditional names here, the base transceiver stations, base station controllers, and the mobile switching stations. And if you can imagine that we have equipment clocks that will transfer the time into the final node. And it could also be that an atomic clock comes directly into or close to the edge or to the final node itself. And if you look at the requirements of frequency synchronization, it is a 50 PBB with respect to the nominal or the central frequency source that we need to have in order to support moving vehicles, in order to support handover. In terms of phase accuracy requirements, we all started with the 3 microseconds across multiple base stations, which translates to plus or minus 1.5 with respect to a common reference sourse. When we moved on to 5G, we can see that this requirement of 1.5 has come down to much smaller numbers, like 130 nanoseconds or so. With 5G, with traditional 4G and previous architectures, the base station was much more closed. We had the base band unit and the radio units connected to proprietary architectures. And as 5G came on, the Open RAN initiative wanted to break the elements in front hall and then make them more open, make them more generic, so that we can have innovation, we can have multi-vendor systems and so on. So that gave the opportunity to look at the processing engines or the baseband units of what we call as the distribution units. Here are the baseband units. So looks like the distribution unit fits very nicely into a data center. So if you look at the way data centers are built, they are mainly done for, or their main strengths are the computing, storage, and the networking, which is actually what is required for the baseband units. And it also provides proximity to the end applications, particularly the URLLC use cases and probably the real-time applications that needs offloading. We can have a data center that is close to the end application or the UE. In applications of private 5G networks, it is similar. We have a very strong computing network that is close to the end application. For example, either it is secure industrial applications or like integrated AI ML applications of the entire 5G networks. Having a data center replacing a DU makes much more sense. Now let's look at the data center architecture and synchronization. I think that has been the topic in the last 2 presentations as well. We can see the general or most common architecture is to have this spine and leaf switches and then connecting to the servers and storage elements. And synchronization is already in place in order to make sure that we have databases being managed, the search functions are optimized, we can deliver contents in real time, and we can provide fast responses to the users. But synchronization performance, as we see, traditionally they are in the milliseconds range, and with the new applications, as David was explaining in the previous slide, it's coming to about 5 microseconds or 2.5 plus minus 2.5. So if you were to transfer or use the data center as it is, that may not be good enough to support the telecom networks directly. Even if you have much less elements from the grandmaster in the network, in the data center into the final node. So if you're assuming that we were able to drive the radios directly from the servers, and if you think that we have the synchronization comes into the data center either through atomic clocks, either through GNSS, or through the network, the performance is still, or the challenge is how to transfer that into the end node and still be able to have this 1.5 if you were to have various radios synchronized to a generic timing solution. As we have seen, there are many ways. The previous presentation talks about, or there are mechanisms to do it through NTP, through PTP, through synchronous Ethernet, through the combination of PTP and synchronous Ethernet is one common way that is used in the ITUT and so on. There are other newer methods. There is data center synchronization protocol itself. There is other methods of distributed time synchronization. Many of the data center people are trying to implement similar architectures. There is a big reliance on GNSS because of the fact that a lot of the brownfield applications or new deployments in this scenario may not have synchronization that is coming from the network side, or the greenfield applications, the entirely new applications may be depending on local data centers, which may not have the right kind of synchronization that is transferred from the data networks that are coming in. That means that there is a big reliance to GNSS, that the data center fundamental clocks are based on GNSS. And that brings in the idea of holdover that David was describing earlier, and that's one of the key points that I want to highlight in this presentation. So holdover benefits actually the network operators. It is actually providing the service continuity, but at the same time, it provides much better user experience to the end customers. So that avoids a lot of savings, or to the operator, that means you can avoid a lot of truck rolls, which means the overall cost of operation, even though you have an additional cost to implement reference clocks to have better holdover, overall cost of operations can be saved significantly. And we have seen some of the performance of the generic clocks in the systems that provide maybe 4 hours, 8 hours, 12 hours with the generic OCXO level clocks. We have new architectures that are coming up where these levels of quartz-based OCXO technologies taking in network or traceable reference clocks, and then compensate the aging part to provide 24 hours of holdover. 24-hour holdover has been one critical or one specific target that many of the operators are looking for. Within 24 hours, somebody is able to recover their operation is something that people are interested to look at. So we have devices that are providing such holdover solutions today that takes in. The key is that the aging is compensated through the traceable reference clock that comes from either an atomic clock or from a network source that is able to handle the compensation part and provide significant performance improvements. Just to show some of the performance graphs here, the red graph, the red line, at the beginning we see a temperature ramp of about 4 degrees, and then the system is still able to hold the phase within 1.5 microseconds across 24 hours is a sample that is shown here. Just to summarize, we can see a big or major convergence of telecom and data center networks, and there is tight synchronization methods that are deployed in data centers in order to support the telecom networks, and we have cost-effective clock references that are coming up in order to provide such solutions today. Thank you very much.
That sounds like a very vague word. When you say tight synchronization, it's like when data center people talk about high availability. It's kind of like a marketing word.
Thank
so
you.
What do you mean by tight synchronization?
Thank you. From a telecom perspective, I think the number that we are looking at today is like 130 nanoseconds. Is a number that we see that either in a dynamic synchronization situation or in a holding situation, the reference to the end node should be within 130 nanoseconds.
And is that a normal distribution or a Poisson distribution?
This is a maximum number that I can see.
A maximum number?
Yes, it's not a distribution.
No long tail on this.
I don't know. I mean, I think some of these definitions that people have done are probably defined across many, many years ago, and it's very difficult to find out exact reasoning. For example, if it is 1.5 microseconds, if you were to find the impact of 1.5 microseconds on the effect of that, it's actually the maximum number that we see. It's not a distribution number.
Thank you.
As I understand. Thank you.
Yeah, so I think I had a quick follow-up on that question. So you said it's 150 nanoseconds, right? So you said you don't know why it's that number?
No, actually, the 3GPP defines these numbers.
Right, so I understand. But do you have an understanding or intuition as to how they come to that specific number? Because I understand it's like the resource block allocations, right? Like that's why your synchronization is very important. So I just wanted to, if you had any thoughts on that.
I only know about the application requirement. This is mainly when we have the carrier aggregation across multiple carriers. We need to have 130. What is the impact of that? I won't be able to tell. I don't know.
Yeah, that makes sense.
Thank you.
And my second question was, so right now it's primarily all like sub 10 gigahertz signaling, right? Like the base stations. But then if you start pushing towards the millimeter wave, 28 gigahertz and above, people make jokes, there'll be more base stations than people, right? Mobile devices, because anyway. So my question is, when you start looking at time synchronizing such a large number of base stations at that accuracy that you mentioned, what are some of the additional challenges that you start to see that needs to be solved?
It will be much more easier to have because you have the possibility of having more mutual synchronization possibilities. Traditionally, all the network synchronization is hierarchical. You have to go from A to B to C to D to E, whereas if you were to have, say, a number of nodes together, and then if you arrive at an equilibrium of time together and then float across that, that might still be good enough for most of the applications. So I feel that it will be an advantageous to have more nodes closer together to get better synchronization.
I see, so more like a peer-to-peer.
That's correct, yes.
Okay, thank you.
Thank you.